You might think linear equations are, just finding x and y on a graph, that kind of stuff from high school algebra.
Yeah, the lines crossing, finding that one point.
Exactly. But what if we told you there are actually two profoundly different yet equally valid ways to see these equations? And one of them, well, it really unlocks the power of linear algebra in our modern data-driven world.
It's this fundamental duality, right?
Yeah.
Once you grasp it, your whole understanding of matrices and vectors, it just takes off.
That's the idea. Today, we're taking a deep dive into this fascinating duality, the row picture versus the column picture.
Two sides of the same coin, really.
Our mission is to unpack these two viewpoints, explore why the column picture is so conceptually powerful, so critical for applications like, say, AI and computer graphics, and then maybe investigate why traditional linear algebra teaching often overlooks this vital perspective, or at least downplays it.
Yeah, why it doesn't get top billing. We pulled together insights from, a range of expert sources for this history of the field, pedagogical studies, and of course the work of mathematicians like Gilbert Strang.
Oh, absolutely. Strang's work is central here. So get ready for some potentially illuminating insights.
Hopefully some real aha moments.
Okay, so let's unpack this. The row picture, this is probably what most of us saw first, right, in early math classes.
Definitely.
You see a system like 2x plus 3y equals 7 and 4xy equals 5. That's the row picture view. A is your matrix of coefficients, x is the unknowns, b is the constants on the right.
You got it. And in this view, each row of that matrix A represents a single linear equation, a constraint.
And the goal is just find that specific point, the coordinates, x, y, maybe z, that satisfies all those equations at the same time.
Precisely. It has to lie on all the lines or all the planes.
So visually, in 2D, it's easy. It's the point where two lines cross.
Right.
In 3D, okay, it's where three planes intersect.
A bit harder to draw, but conceptually the same.
And then in higher dimensions you're looking for the intersection of multiple hyperplanes, which are, well, they're just the n-dimensional versions of lines or planes.
Yeah, the geometry gets abstract fast, but the idea is the same, finding that single common point.
And the main algebraic tool we learned for this is usually Gaussian elimination.
That's the workhorse, a systematic process to rearrange the equations, simplify them, usually into an upper triangular or row echelon form, so you can just read off or back substitute to find that intersection point.
It works. It's robust for calculation, but I always found, visualizing it beyond 3D gets tricky.
Impossible, really, for our brains.
Yeah, and it also makes the matrix A feel a bit static, like just a box holding numbers.
That's a really good point. It emphasizes the constraints, the equations, maybe less the matrix itself as an active object. Powerful for finding the solution, maybe less intuitive for the bigger picture.
Okay, now, here's where it gets really interesting, I think. What if there's another way to see XCB that completely flips the script?
This is the column picture. It's something people like Gilbert Strang have championed, and for good reason.
So how does it work? How do you reinterpret XB?
Instead of seeing multiple equations, you see it as a single vector equation, the whole thing.
A single equation. How?
The fundamental question changes. It's not where do these line splines intersect anymore. It becomes how can we find a linear combination of the column vectors of matrix A to produce the target vector B.
Whoa, okay. Linear combination of the columns of A. So the unknowns by 1, by 2, etc. They're not coordinates anymore.
Exactly. They transform. They become scalar weights or coefficients. They tell you how much of each column vector you need to add together.
So like take I1 times the first column vector plus by 2 times the second column vector and so on.
Until you hopefully build the vector B on the right-hand side.
Huh. So the geometry totally changes too. It's not finding a point.
Nope. It's about building or synthesizing. You start at the origin, and you use the column vectors as directions. The x values tell you how far to go along each direction, stretching or shrinking the column vectors.
And the goal is to land exactly on the target vector B.
Precisely. This makes the matrix A feel much more dynamic. It's like an operator or a transformation. It takes the input vector x, the weights, and produces the output vector B by combining its columns. It's a profoundly different feel.
It really is. Okay, so we have these two ways of looking at the exact same system, XB. How do they really compare conceptually? What's the essence of the difference?
Well, even though they describe the same algebra, their conceptual weight and geometric feel are worlds apart. It's this core duality.
Okay.
The row picture focuses on finding a solution under constraints. You're looking for that one point that satisfies all the conditions.
Right, living on all the lines or planes.
While the column picture focuses on synthesizing to achieve a target, you're actively building vector B from the components provided by the columns of A.
So if the row picture asks, is there a point on all M hyperplanes? The column picture asks, can vector B be created by linearly combining the n column vectors of A?
That's it exactly. And look how everything shifts.
Okay.
Row picture sees matrix A as rows, each defining an equation or hyperplane.
Got it.
Column picture sees A as columns, serving as building blocks in a vector space.
Right, the directions you can move in.
Vector X solution coordinates in the row picture.
Becomes scalar weights in the column picture.
Yep. And vector B, just a set of constants defining the equations in the row picture.
Becomes a single target vector you're trying to reach in the column picture.
It's a complete perspective shift, geometrically.
Yeah.
Intersecting shapes versus vector addition. Scaling, spanning space, algebraically. Gaussian elimination versus thinking about linear combinations and vector spaces.
It really is like looking through totally different windows at the same room.
Wow.
And
Yeah.
you're saying this column picture isn't just like a neat alternative view. It actually leads to deeper, more useful concepts in linear algebra.
Oh, absolutely. It's the natural pathway to some of the most powerful ideas. It directly gives rise to the concept of the column space of a matrix A, usually written CA.
The column space, okay, what is that exactly?
It's the set of all possible vectors you can create by taking linear combinations of A's column vectors. Think of it as every single destination vector B that you could possibly reach using the columns of A as your building blocks.
So it's the space spanned by the columns.
Precisely. Geometrically, it's the image or the range of the linear transformation that A represents. It's the entire universe of possible outputs.
And this connects back to solving axis B.
Beautifully, it leads to this incredibly elegant condition. The equation axis B has a solution if and only if the target vector B is actually in the column space of A.
If D is reachable using the columns.
If it's reachable. If it's not in CA, no combination of the columns will ever get you there. No solution exists.
That's a huge insight. Instead of just testing one B at a time with elimination.
Right. The row picture asks, does this specific system have a solution? It's very particular.
Yeah.
The column picture, by forcing you to think about the column space, asks a much deeper question. What is the entire universe of B vectors for which any system with this matrix A will have a solution?
Wow.
Understanding CA once tells you about the solvability for any B. That's a massive conceptual leap. It shifts from calculation for one case to understanding the possibilities for all cases.
So it helps make really abstract ideas feel tangible, more geometric.
It absolutely does. Take linear independence. It can feel a bit definition heavy sometimes.
Yeah.
But in the column picture, it's very visual. A set of column vectors is linearly independent if no vector in the set can be written as a combination of the others.
Meaning each one adds something new.
Exactly. Each one points in a genuinely new direction, adding a new dimension to the space they span. Think of two vectors in 3D space that aren't parallel. They define a plane, right?
Right.
A third vector is linearly independent only if it points off that plane. It adds the third dimension.
Okay. And if they're dependent?
Then at least one vector is, well, redundant. It's already lying within the space span by the others, like that third vector lying on the plane defined by the first two. Adding it doesn't expand the space. It doesn't add a new dimension.
I see. That connects to solving X0, doesn't it? The homogeneous system.
Directly. If X has a non-trivial solution, meaning a solution where X isn't just all zeros, what does that mean in the column picture?
Oh, it means you can combine the columns of A using those non-zero X values as weights.
And get the zero vector, which is the very definition of linear dependence. The columns aren't independent if you can combine them to cancel each other out.
That makes sense. And concepts like span and basis.
They flow naturally from this picture. The column space, CA, is the span of the column vectors by definition.
Okay.
And a basis for the column space is just the smallest possible set of those column vectors that can still span the entire column space. And crucially, that set must be linearly independent. It's the minimal set of building blocks.
And rank. I remember that term.
Rank comes straight from this too. The rank of matrix A is simply the dimension of its column space.
Ah, so it's the number of vectors in the basis, the number of linearly independent columns.
Exactly. It's the true dimension of the output space that A can actually reach. All these core concepts, independence, span, basis, rank, they feel much more integrated and geometric through the column picture lens.
It seems like this column space idea is really central. You mentioned Gilbert Strang. Doesn't this lead to his idea of the four fundamental subspaces?
Yeah.
Like a grand unified theory for matrices?
It really is the gateway to that. The column picture naturally leads you to think about spaces associated with the matrix, and Strang's framework elegantly lays out the whole structure.
Yeah.
These four subspaces give you a complete picture of the linear transformation A.
Okay, can you give us the quick tour? What are the four?
Sure. You have the column space,
Mm-hmm.
which we've been talking about. All possible outputs, all linear combinations of the columns. It lives in the output space, say arm, if A is m by n. Its dimension is the rank.
Right, the reachable outputs.
Then you have the null space. This contains all the input vectors x that get mapped to the 0 vector by A, so x is 0. These are the inputs that A effectively squashes or destroys. It lives in the input space, Rn, and its dimension is nr.
Inputs that go to 0? Okay.
Go more. Then you flip things around by looking at the transpose, At. The row space, Cat, is just the column space of the transposed matrix. It's the space spanned by the rows of the original matrix A. It lives in the input space, Rn, and its dimension is also the rank, Rn.
So spanned by the rows, lives in the input space. Got it.
And finally, the left null space,
Mhm.
Nat. This is the null space of the transpose. It contains vectors y such that At equals 0. It lives in the output space, Rm, and its dimension is Nr.
Wow, okay, so these four spaces completely carve up the input and output spaces associated with A.
They do. The row space holds the inputs that actually get transformed into something non-zero.
Yeah.
The null space holds the inputs that get sent to 0. The column space holds all possible non-zero outputs.
Hmm.
And the left null space, well, it relates to constraints on B for solvability, but the key is the structure.
And the really elegant part is how they relate geometrically, right? The orthogonality.
That's the beautiful connection, often called the fundamental theorem of linear algebra, part 2. The row space is orthogonal to the null space. Every vector in the row space is perpendicular to every vector in the null space.
Okay.
And similarly, the column space is orthogonal to the left null space.
That geometric picture, perpendicular spaces partitioning the input and output, seems much easier to grasp when you're thinking in terms of vectors and spaces, like the column picture encourages.
It really is. The row picture, focusing on intersecting hyperplanes, doesn't naturally lead you to visualize this complete, elegant, orthogonal structure in the same way. The column picture sets the stage for it perfectly.
So this isn't just, abstract mathematical beauty. You're saying the column picture is actually how linear algebra gets used in the real world, in modern tech.
In many, many crucial applications, yes.
Yeah.
It's the most natural way to think about it. Take computer graphics.
Okay.
3D models are basically collections of vertices, right? Points in space,
Yeah.
vectors. When you want to rotate an object or scale it up or shear it, what are you doing mathematically? You're multiplying those vertex vectors by a transformation matrix.
Right. A matrix does the rotation or scaling.
But how? The column picture gives you the intuition. The columns of that transformation matrix are incredibly important. They tell you where the standard basis vectors, like your initial x, y, and z axes, end up after the transformation.
Oh, interesting. So the columns show the transformed axis.
Exactly. The first column of rotation matrix shows where the original x-axis points after the rotation. The second column shows new y-axis direction, and so on.
Okay.
So when you compute A, matrix A times vector V, what are you doing from the column picture perspective? You're taking a linear combination of those new basis vectors, the columns of A.
Using the coordinates of your original vector V as the weights.
Precisely. It tells you how to express your original point V in terms of the new transformed coordinate system. That's the most intuitive way to understand what a geometric transformation is. It's fundamentally changing the coordinate system.
That makes sense. Even complex things like perspective projection.
Yep, even homogeneous coordinates used for translation and perspective, they build directly on this idea of transforming the basis vectors, which is the essence of the column picture view of matrix multiplication.
Okay, graphics make sense. What about something totally different, like machine learning, AI?
Hugely important there, too. Think about one of the most fundamental techniques, linear regression.
Right, fitting a line or plane to data.
Exactly. You're trying to predict some target variable y based on a set of input features x. You model it as y being approximately a linear combination of the features. We write it as xey.
Okay, X is the data matrix, AQR is the weights or coefficients we want to find, Y is the target values.
Now look at that expression x. What is that from the column picture?
It's XER2 times the first column of X plus XE2 times the second column of X. It's a linear combination of the columns of X.
Exactly. The columns of your data matrix X are your feature vectors, like height, weight, age, whatever. The expression X is literally building a predicted vector by combining those feature vectors using the weights in the make.
Huh, okay.
Now, here's the key connection. In almost any real-world data set, your actual target vector, your day, won't lie perfectly within the column space of X. There's noise, the model isn't perfect, there's no exact solution for big.
Right, the data points are never perfectly on the line.
So what does linear regression, specifically ordinary least squares, do? It finds the vector, let's call it y hat, that is in the column space of X and is as close as possible to the actual Y.
It finds the best possible prediction within the space spanned by the features.
Exactly. And that closest vector y hat is the orthogonal projection of the actual Y onto the column space CX. The entire conceptual foundation of least squares regression is deeply geometric and relies heavily on understanding the column space.
Which the column picture makes intuitive.
Precisely. It frames the problem as projecting the target onto the space spanned by the predictors.
Okay, so this column picture seems incredibly powerful conceptually and super relevant for modern applications like graphics and machine learning. Which brings us back to the question, why do most linear algebra courses tend to start with, and often really hammer home, the row picture?
Yeah, it's a great question. Part of it, honestly, is just history. The way we often teach math mirrors the way the subject itself developed over time.
How so?
Well, the earliest glimmers of linear algebra, thousands of years ago, think Babylonian clay tablets, ancient Chinese texts, they weren't about abstract vector spaces. They were about solving systems of 2 or 3 linear equations to get practical numerical answers for things like trade or resource allocation.
So very concrete calculation, row picture thinking, essentially.
Very much so. Find the unknown quantities that satisfy these conditions. Then, much later, 17th to 19th centuries, you get mathematicians like Leibniz, Kramer, Gauss, developing more systematic methods, determinants, Gaussian elimination, still focused on solving systems, finding that intersection point.
The matrix itself wasn't really the central object yet.
Not in the modern abstract sense. The term matrix wasn't even coined until 1848 by J.J. Sylvester. Arthur Cayley developed matrix algebra in the 1850s. And the fully abstract axiomatic definition of a vector space wasn't really nailed down until the 1920s.
So the abstract stuff, where the column picture feels more natural, came much later historically.
Much later. So it's kind of natural that curricula often start with the oldest part, solving systems via elimination, row picture, and then gradually introduce the more modern abstract concepts like matrix operations, vector spaces, linear combinations, column picture, later on. It follows the historical path.
Did the computer revolution after World War II shake things up? Computers seem tailor-made for matrix calculations.
Oh, significantly. Suddenly, solving really large systems of linear equations became feasible, and it was essential for physics simulations, economic modeling, engineering, all sorts of things.
So that must have pushed for changes in teaching.
It did. There were calls for reform. In fact, back in 1990, a group called the Linear Algebra Curriculum Study Group, LACSG, put out influential recommendations. They strongly advocated for a matrix-oriented core curriculum, precisely because matrices and matrix computations were so crucial for science and engineering majors using computers.
So did they recommend starting with the column picture then?
Not explicitly starting with it necessarily. What happened was sort of a compromise. Courses definitely became more matrix-oriented. Lots of matrix multiplication, inverses, determinants powered by computational tools. But they often kept the row picture via Gaussian elimination as the primary starting point and core algorithm.
Why, if matrix operations were key?
Probably because elimination felt more concrete, more algorithmically straightforward to teach and learn initially, and it tied back to that familiar high school algebra. So many courses became focused on matrix methods for solving systems, still rooted in the row picture logic, rather than starting fundamentally from vector space theory, where the column picture shines.
Okay, so history plays a big role. Are there also purely pedagogical reasons, like teaching strategy reasons, for starting with the row picture?
Absolutely. Several compelling ones, actually.
Like what?
First, familiarity and concreteness. Like we said, 2x plus 3y equals 5 looks like something students have seen before. It connects to prior knowledge.
Whereas x times 2, 4 plus y times 3, negative 1 equals 7, 5.
Exactly. That column picture version by 2 divided 4 plus y3 des 1 equals 7, 5 immediately requires a conceptual leap into vectors. Scaling, adding them, it's more abstract right out of the gate.
Makes sense. What else?
Gaussian elimination provides a very clear step-by-step procedure. It's an algorithm, a recipe. Students can follow the steps and get an answer, which builds confidence early on.
Yeah, you feel like you're doing something concrete.
Right. Starting with abstract concepts like span or basis or linear independence, without that concrete computational anchor can feel very overwhelming and disorienting for many introductory students.
And then there's just inertia.
Curriculum inertia is huge. Educational systems are conservative by nature, textbooks are written, lesson plans are developed, instructors gain expertise, all based on the traditional row-first sequence.
So changing to a column-first or even a truly parallel approach requires a massive effort.
A huge overhaul of resources, potentially retraining instructors. It's a big lift. So the very abstraction that makes the column picture so powerful conceptually also makes it a steeper initial climb. Pedagogy often favors starting with the most tangible entry point and gradually increasing abstraction. For systems of equations, that tangible start is usually seen as the row picture.
Okay, so it sounds like it's not really about one picture being right and the other wrong. They both describe the same math.
Exactly. It's not verses in the sense of a battle. It's about duality.
The real goal is to be able to switch between them.
That's the mark of true understanding. Being able to fluidly move between both perspectives depending on the problem. The row picture is fantastic for understanding elimination, the mechanics of solving, and the structure of solutions, like when you have free variables for max zero.
Right.
But the column picture is absolutely essential for understanding why solutions exist, column space, what transformations do, and for connecting linear algebra to geometry and applications like projection in machine learning.
So the failure isn't teaching the row picture.
Not at all. The potential failure is neglecting to introduce the column picture early and elevate it to equal conceptual importance. Students need to see explicitly that finding intersecting hyperplanes and building a target vector from column combinations are just two different, equally valid ways to describe the same underlying mathematical reality.
So for our listeners learning or maybe relearning linear algebra, what would a more modern integrated approach look like? How could they get the best of both worlds?
I think a modern approach needs to leverage a few things. First, integrate computation right from the start.
Using tools like Python or MATLAB.
Exactly. Python with NumPy, MATLAB, Julia, whatever. These tools let you visualize and experiment immediately. You can plot vectors, see linear combinations add up, watch transformations happen. This makes the abstract ideas of the column picture span linear independence feel much more tangible and interactive. Less abstract symbol manipulation, more geometric intuition building.
That sounds way more engaging.
It can be. Second, make it application-driven where possible. Instead of just, here's the theory, maybe we'll use it later. Start with a motivating problem.
Like the computer graphics example.
Sure. Start by showing how matrices rotate points that immediately highlights the column picture view of transformations. Or start with a simple data analysis problem that naturally leads to the idea of projecting onto a subspace, going in the column space. Use the application to motivate the theory.
And you mentioned visualization.
Yes. Promote active and visual learning. Move away from just static lectures. Use simulations, animations. There are amazing online resources now, like the videos by 3 Blue 1 Brown, that are fantastic for building geometric intuition.
His Essence of Linear Algebra series is brilliant for this.
It really is. The column picture, being so inherently dynamic and geometric, is perfectly suited for these kinds of visual interactive learning methods.
So the ideal curriculum would introduce both pictures, maybe side by side, right from week one.
That would be the dream, I think. Take a simple 2x2 system, solve it using elimination, that's your row picture. Immediately afterwards, draw the two column vectors on a graph. Show how finding the solution x and y is the same as finding the weights to combine those vectors to reach b.
See both geometric interpretations at once.
And maybe even have students tweak the numbers in code and see how both the intersection point and the vector sum change in real time. That kind of parallel, computation-driven visual approach. That's how you unlock the full power and beauty of linear algebra for everyone, especially the next generation of scientists, engineers, data analysts.
It's a powerful vision. We've gone from, ancient Babylonian equations to AI and computer graphics just by changing how we look at XB.
It's amazing, isn't it, how these two seemingly simple pictures, intersecting lines versus combining vectors, unlock such deep insights into both abstract mathematical spaces and incredibly practical technologies. Understanding these duality really helps you grasp the core of how so much of our digital world is built, how complex systems are modeled and operate.
So maybe a final thought for everyone listening. Consider this. How many other concepts in your own field, or even just in daily life, that seem straightforward might actually hide these kinds of profound dualities? Are there places where finding a different picture, a different perspective, could completely transform your understanding?
Yeah, what other areas could benefit from deliberately seeking out and embracing multiple viewpoints? You might uncover a much richer, deeper truth than any single perspective could ever reveal on its own. It's a powerful way to think.